you know the displacement model in this fashion, expressed in terms of a known nodal displacement through shape function. You can find strain, which is derivative of this, right? Derivative of this means it is only derivative of shape function. Then stress strain knowing energy, which is integral form, integration, then again integration of shape function, then minimization of that will give you element properties. So that is the simple steps involved in that. Now I have completed the second step, displacement model. Now third step, element property. Strain, stress, then element stiffness matrix. I will do that element stiffness matrix for this bar or flux element and prove it. So the element stiffness, what time is there? Just third step. Element property. That is stiffness, member stiffness matrix. Km determination. So, U is equal to, we know, U is equal to N Q. That just now I explained displacement at any point U for bar or this element property for bar or stress element. Element property, local coordinate, mind it. Each and every word is important. It is element property means in local coordinate, Km only I am writing, not global. Local coordinate. So local coordinate, this natural coordinate system is also a local coordinate system. I told I will use both. Taking origin only at the center of element. In local, it is one end. Instead of one end, I will take origin. It doesn't make any difference. It only ratios of displacement from anywhere we can take it. There won't be any confusion at all. That's why we are resorting to natural coordinate system. We know that this already I have derived. Now, strain epsilon is delta u by or du by dx, I would say, from elasticity for bar or stress element, du by dx. Rate of change of this. It is derivative, differentiation. So that is nothing but dn by dx. Q is after all nodal displacement vector, right? It is a value, it cannot be differentiated, it is a constant, correct? Displacement vector. If you find that it will be zero. So, if at all we have to derive, it is only this. So, this dn by dx is nothing but dn1 by I will say d1 by dx. You can write it as d1 by d psi by dx. I will convert it into natural coordinate system. Because d psi cancel, it will be same as d by dx. What is d psi by dx? I can find d psi by dx. D psi by dx, this psi is after all, I told you, ratio of x by x dash. That is local coordinate system length. So d psi by dx or dx dash are the same here. Local coordinate system or global coordinate is the same x. direction. Right? What is this dx dash by dx? dx by dx dash or dx is 2 by n. Right? This is important, and that's why I told you always you have to remember this. dz by dx. If the derivative becomes very, very simple, it is only this. Now I can derive it, find the derivative of this n by z. Because dz by dx I have already determined. dz by dx is x or x dash, their moment is same, is. That's an important property. You have to remember. It is always 2 by n. In further also, beam problem also, and be using this. Right? You remember this property. One is defining natural coordinate system and its derivative with respect to local coordinates. Local or global, they are one and the same. You can take it here. So it is, that is 2 by n. dn by dz is dn1 by dz and dn2 by dn2 by dz. n is nothing but n1, n2. So that is nothing but therefore dn by dx or dn by dz is minus half. dn1 by dz is minus half. dn2 by dz is plus half. That's why I told you it's very simple. Knowing that. So it is minus half. This 2, if I take it outside, I'll get. See how simple it is now. So therefore, strain is nothing but 1 by L minus 1 into Q. That is Q1, Q2. Nodal displacements. This is called strain displacement matrix. As the name itself indicates, this is the displacement, this is the strain, this is the connecting matrix. Strain displacement matrix. This is called PQ, where P is called strain displacement matrix. Very simple. After knowing shape function, displacement model you will write, then strain. From elasticity, you write the expression for strain. Then stress within the elastic limit, it is the constitutive matrix into strain. Sigma by epsilon is nothing but your modulus of elasticity. Modulus of elasticity is called C. Constitutive or elasticity, modulus of elasticity matrix, which is basically material property known for plane stress problem, plane strain problem, axis symmetry problems, as well as this one-dimensional bar constitutive matrix is known. Here it is only E. C is only a 1 by 1 matrix, E is the only value. So, that is nothing but E epsilon. Or in general, constitutive matrix you have to take. I am writing the general procedure, displacement model from that strain using the relationship, the strain displacement relationship, then stress using strain displacement relationship, or strain stress relationship. Stress strain relationship, strain displacement relationship, this is where that elasticity comes into picture. Application of theory of elasticity for finding element property, nothing other than that. Having determined displacement model in step 2, while determining the element property, this elasticity you will use. It's a 2D elasticity, 3D elasticity, or 1D elasticity. Nothing other than that. It's only elasticity thing. Then, after knowing strain, stress, you can find stiffness. So, we know potential energy I is equal to U minus W, where U is strain energy, because within the elasticity limit, strain energy is given by half epsilon T sigma. I am writing transpose because they are both are of same order. Epsilon and sigma, one should be multiplied by other when it is transposed, when they are of same order, into dV over the entire volume of the bar. That is the strain energy, and W is nothing but external gun. That is nothing but if you have a load in the bar, say P axial load, for that displacement will be there. That displacement is U I am taking, a UD, PD or the displacement, nodal displacement. So this you can see P load vector into corresponding displacement vector Q, PQ. So you substitute, you will get phi is equal to U is V half epsilon T sigma. I have avoid making this your matrix notation. Otherwise you can write sigma T epsilon dV minus T Q. You substitute epsilon and sigma. You will get half epsilon T is nothing but BT QT. Correct? BT QT. That is epsilon. Epsilon is PQ, where B is the strain displacement matrix. That's known. And sigma, that E into strain, that E constitutive matrix into strain, B into Q. Correct? B into Q, sigma. dV is nothing but A into dl. A is the area of cross section uniform for the bar or truss element. dl is small length. I have to integrate it. Instead of V now, I can change into line integral. This is from dl, I will say dz. Because this dA is in terms of psi, we have defined. Correct? This in natural coordinate system, I have to say d. This I can say dl, I can say 2 by L into dz. Because I told you that important relationship, always the ratio I have to say 2 by L into d psi. This x dash, I told it is nothing but psi by n by 2. Therefore, that dx or dl, both along length direction only, it is 2 by L d psi. That relationship you have to remember, I told. So that is 2 by L, we have to take it. Not just simply converting that global integration to natural integration. This is that change in global to natural coordinate system. This, it was dl, that is global or local, whatever it is. That integral I am changing into natural by using this. We know relationship between local or global to natural. It is just a ratio. So therefore dx of this is dz by L by 2 or 2 by L. L by 2, I will take it 2 by L. That's all. Always this you are forgetting, that you should not forget. Now we can integrate it. Of course, that integration formula, you don't have to worry straight away. You can integrate it now. It is between the limits -1 to +1. Because the moment you have changed this, it is that. So that pi is equal to last step of, you can remember this formula straight away. bt, this is your C, this is qt, bt, this b, I write first, then this is qt, q. One is from strain, another from stress type. So this is A into integral of d psi. D psi integral is psi between limits -1 to 1. That is 2. Correct? Upper limit, this is psi. Upper limit 1 to -1. 1 minus of -1, it is 1 plus 1. This will be 2 straight up. So this integration will become 2. Or with this you can remember, this is my stiffness, Bt, integral Bt Eb, general stiffness equation. So now I will apply before integration, let's say from minimum, okay, and of course this term I avoided, minus W, minus PQ I have written here. Here I didn't carry. That's all. The same PQ it will be carried. So now from minimum potential energy, this delta partial derivative of this with respect to Q variable has to be minimum. Minimum means first derivative must be 0. First derivative with respect to displacements. Here QT means it is Q square. Correct? QT into Q is Q square. Derivative of Q squared is 2Q. That 2 and this 2 cancels. So you have only therefore integral Bt dB Q minus, here while integrating this will be 1. It is minus P. That should be 0. Or I can say, and of course A dz A dz. And 2 by L. So from this we can say P is equal to K because integral of this dz A into dz, it is length itself. This total integration A dl is nothing but volume. So you can say A into L, and that L and this L get cancelled, and you have to write this, and these two in this -1 to 1 when you are taking. So that this is, I think it has to be, these two get cancelled. So this is another 2, and there must be one more 2 somewhere. This from integration 2, that 2 will get cancelled, but the other 2 is there. Okay? From this 2, it has to cancel from this L and L. If you take A, this A by L somewhere here, I have here L, 1 by L. If you substitute for B and B, you will get denominator 1 by L, and that will be cancelled by this. One is BT, one will cancel with another. Finally, you will get this K as K is equal to this K as integral -1 to 1 of this. You will get AE by L, and that limit B after substituting will get this. This final, I will work it in the next class. From here onwards, I will work in the next class and prove that K will be AE by L 1 minus 1. Alonso.